Hi everyone, so in this video we'll discuss the sigmoidal output units that are used for Bernoulli distributions. Bernoulli distributions means it's basically used for two-class classification problems, right? So let's recap from last time. So from last time we had that we discussed the cross-entropy cost, right? And we reached the conclusion that the cross-entropy cost that is based on the maximum likelihood principle is basically a negative expectation, empirical expectation over x and y of log p model, the conditional distribution of y given x and the parameter state, right? But we also discussed that a desirable property of gradient-based learning, which is used in deep neural networks, is to have the gradient to not saturate, meaning that we want the gradient magnitude to always be significant, right? And log functions can easily saturate unless they are combined with exponentials so that you get a linear output, right? So log e to the x is x, but log anything else can easily saturate, right? So we are considering two-class problems. So what we need from the output unit is that this output unit estimates the probability of y equal 1 given x, right? So only one output unit is sufficient because you have a binary variable, right? And that's what it means by Bernoulli distribution. This variable can only take 1 or 0. So if we estimate probability of y equal 1 given x, then we automatically have the probability of y equals 0 given x, right? So we have a neural network, and this neural network processes values, and then until we reach the layer before the last layer, right? And then from the layer before the last layer, we have some nonlinear activations, say rectified linear units that we discussed them for the XOR example. And then we have weight multiplication and then adding bias, and then we get one output unit which corresponds to the sigmoid. Now, this output unit will then be processed through the cross-entropy cost. Now, the first thing that we want from this output unit, if it were to estimate the probability of y equal 1 given x, is to have its value between 0 and 1, right? So we want to bound the value between 0 and 1. The naive approach to do this is basically to take the maximum of 0 and the minimum of 1 and the value of the output unit, which is W transpose H plus B. So we call these units the hidden activation output of the layer before the last layer. We call it vector H, right? And W transpose, this is a vector representing the values of W1, W2 up to W of the magnitude of H plus the bias, right? So the naive approach is basically to bound it. If it's less than 0, then make it 0. If it's more than 1, then make it 1. Right? But this is bad because it saturates when you are out of bounds. So for example, if the value of the output unit is -2, there is no learning that happens because the value of the cost function doesn't change whether the value of the output unit is -2 or -1.5 or -1 or -3, right? So the gradient saturates. The gradient is 0 out of bounds. So that's a problem. So what happens with the sigmoid function is that it's a continuous approximation of this bounding function, right? So basically sigma of z equal 1 over 1 plus e to the minus z. So the sigmoid of any variable z equal 1 over 1 plus e to the minus z. So if z is very negative, then e to the minus z goes to infinity, then you have a 0. If z is a large positive value, then e to the minus z goes to 0, then sigma of z becomes 1, right? So it's between 0 and 1, but it's a continuous function, right? So it's not flat even for large positive values of the parameter z, and it's not flat even for large negative values of the parameter z, right? So we approximate p of y given x by sigma of 2y minus 1 times z. So if y equals 1, this is sigma of z. If y equals 0, then this is sigma of minus z. So you can think of the probability of y equal 1 given x by sigma of z, the probability of y equals 0 given x by sigma of minus z. So if z is very negative, if z is negative, then it's more likely than y equals 0. If z is positive, then it's more likely that y equal 1. Okay? Now let's see how do we do this, or what's the justification of setting probability of y equal 1 given x to be sigma of z. So we want the logarithm. So remember, this output unit will be processed by the cross entropy cost, right? And the cross entropy cost depends on the logarithm of the value. So we want the logarithm of the unnormalized probability, meaning that we will normalize it later, making probability of y equals 0 plus probability of y equal 1 to be equal to 1. But since we don't initially have control over this on the output unit, so the log of the unnormalized probability, we want this to be equal y times z, right? Why do we want to do this? Where z is the output unit. So if y equal 1, we want this log to be equal to z. If y equals 0, we want this to be 0, right? So basically the value of z, or the value of the output unit, we wanted to represent the log of the unnormalized probability that y is equal to 1 given the input vector, right? So we want to do this because this is good for learning. Because z is a linear function, the gradient is consistent, the gradient doesn't saturate. So it's good for learning that my conditional probability is estimated by the actual value of the output unit, right? Okay, because then the gradient of the cost with respect to the value of the output unit, z, is basically the gradient of a linear function, right? And as we'll discuss later, when we compute the gradient with respect to the parameters, we first compute the gradient with respect to the output unit, right? Through what's called backpropagation. So then p tilde of y given x equal e to the yz. Then p of y given x equal e to the yz over the sum of all possible values of z, e to the yz bar. Right? Now, if you compute this, this is exactly the same as sigma of 2y minus 1 times z. And this is the justification of why we estimate py given x as sigma of 2y minus 1 times z. Right? So here, if y equal 1, you have e to the z over 1 plus e to the over 1 plus e to the z. If you multiply by e to the minus z on both on numerator and denominator, you get 1 over 1 plus e to the minus z, which is sigma of z. If you set y equals 0, then you will find that this is equal sigma of minus z, because you get 1 over 1 plus e to the z. So when processing one example, right? So here I have small x to represent one realization of x. The cost corresponding to that example will be equal minus log of p of y given x. And we said that we are estimating this by sigma of 2y minus 1 times z. Now this logarithm, this value here, equals what's called soft plus of 1 minus 2y times z. And soft plus of x is log 1 plus e to the x. Whenever we say the word soft of a function, we mean it's a continuous approximation of a function that's not differentiable, right? And continuous, so it will be differentiable, so we can handle it with gradient-based learning, right? So this soft plus is a continuous approximation of the plus function, and the plus function will pass positive values unaltered and sets the negative values to 0. And here log 1 plus e to the x looks like this. It's not exactly passing positive values unaltered, but it's an approximation of this. It doesn't exactly set all negative values to 0, but it's an approximation of it. Now, if we look at this cost function, if z is positive and y equals 0, then the gradient tends to be approximately 1. So it will push z downwards. Right? And that's what we need to do. If y equals 0, we need z to be negative. If z is negative and y equal 1, it will push z upwards, right? In a way that has a consistent gradient direction, which is good for gradient-based learning, right? If we have the right answer, then the gradient is close to 0. And remember, this is not saturation. This is a good thing, because if you have the right answer, you don't want to change that answer, or you don't want this example to contribute in a significant way to the cost function, right? Thank you.